energy and power, number 15. This time we're given a velocity time graph. We're asked to draw the corresponding acceleration time graph. So the first thing we need to do is work out what those acceleration values are. Using the data in the graph, we can see that from 0 to 4 seconds, then the acceleration is 2 minus 0 over 4 equals 0.5 meters per second squared. From 4 to 10 seconds, according to the velocity time graph, it's a horizontal line. That means it's not accelerating. That means it's a constant speed. So we can just plot that down as 0 meters per second squared. And then for 10 to 12 seconds, A equals V minus U over T. Let's see, so it starts at 2, it ends up at 0, and it takes 2 seconds for that to happen. All of these numbers coming from the graph. So that would be a deceleration of minus 1 meter per second squared. Now, normally we would say a deceleration of 1 meter per second squared or an acceleration of minus 1 meter per second squared. Normally we would not say a deceleration of a negative value because, as we all know, two negatives make a positive, and if we start speaking like that, we're just going to confuse people. So try to avoid that. Now, the graph that we're asked to draw should then look a bit like this. Get the time axis sorted out first. 0 to 4, so there's 0. I'll call that 4. To 10 seconds, I'll call that 10. And then to 12 seconds. This is not very well done to scale, but it's good enough to show what we need to show and answer the question. At 0.5 meters per second squared, there is our acceleration axis. So, from 0 to 4 seconds, it has an acceleration of 0.5 meters per second squared, so that's going to go across like so. And then from 4 to 10 seconds, it's going to have an acceleration of 0. So I'm going to draw that along the axis where it belongs. And then from 10 to 12 seconds, it's going to have an acceleration of negative 1. So that's going to be round about here. And this is where it's not hugely realistic because nothing changes except velocity that fast. So I'm going to do dotted lines like so, and there's our graph done. And now for part B. So we're going to use our tension formula again, and it's important to note that the lift is moving downwards. So that's going to have an effect on whether we add or whether we subtract. So have a good think about this. We've got 4 kilograms times 9.8 for gravity. We calculated that it was accelerating at 0.5 meters per second squared, but it was accelerating downwards. So that's going to be negative 0.5 that we add on, and as we know, adding a negative 0.5 is the same as taking away a positive 0.5. And that will eventually give us 37.2 newtons. Between 4 and 10 seconds, that's the easy bit, it's not accelerating, so 4.0 times 9.8 plus 0 equals 39.2 newtons. That look a bit more like a 3. And then from 10 to 12 seconds, 4 kilograms again, times 9.8 for gravity again, and it was decelerating, it was minus 1, but it was decelerating downwards. Decelerating downwards, double negative. So we're adding it on this time. If you think again about being at the top of the lift shaft and letting the lift go down through your hands, letting the cable go through your hands, again, ignore the fact that this would rip your hands to pieces. If you're trying to decelerate the lift and it's going downwards, then the lift is pulling away from you and you're pulling upwards. So there's got to be an increase in the force. There's got to be an increase in the tension there. So we have to add it on. And that's going to give us 43.2 newtons. And that's that one.